Hello, everyone. It's now time to start our last big plenary meeting. And first I will introduce me, for those who didn't know me yet. I am Catherine Jandel, and I am the co-chair of the Organizing and Science Committee of this Goldschmidt Conference with Carmen, who is somewhere here. We still have a lot of wonderful talks this afternoon, so please don't leave after this plenary session. And the conference is not over yet, but this is our last plenary. So I want to take the opportunity to say some thank you. The first people I want to thank is all of you for participating in this Goldschmidt conference in Lyon and remotely. We have welcomed over 500 delegates this year, 3,300 in, 3,300, I'm sorry, in Lyon and 700 remote. We thank you all for making this week such a wonderful and friendly event. I hope you all had a great time and heard some exciting science. In addition to great science this week, we have also had some fantastic social events. As you can see on the photos, Goldschmidt Rocks at Ninkasi really rocked. That was, for those who were there, a very wonderful moment, and including for me. This was an exceptional experience. We also enjoyed a fantastic fellow ceremony and reception on the rooftop of the Congress Center. Last night, we had a wonderful banquet in the stunning Palais de la Bourse. And for those who stayed tonight, we called the Mayor of Lyon and we ordered the fireworks, and we got it. And it started at 10:30. Followed by dancing in many places in Lyon. We have added information on the website about where to go. Now, because we are scientists and love statistics, here are a few numbers. I won't go through them all, but it's impressive to think that we managed to fit over 25 oral presentations and nearly 1,600 poster sessions. Presentation into 1 week, not session, presentations. Such accomplishments requires a big team, including many volunteers. So I want to thank the members of the organizing and science committees who worked all the year long, 2 years long, to prepare this conference, including the SIM chairs and all the conveners, and of course, the student helpers here. So please applaud them. But last but not least, I want to give a very special thanks to a team of people who work really hard to make this conference a success. And I cite the member of the GPDL, Adriana, and your colleague. Could you come on stage, please? Wow. The Confex staff, Tracy and your team. So Confex are the people who allow the remote working so well in all the room, so you can also applaud them. Confex and GPDL. And of course, Mario and Alice, our wonderful, exceptional EHG staff. Oh, guys. You are all so great. There is no man, so I say, guys, women, you have been so great all along these days. Yeah, you can applaud them again, please. Thank you very much. The Goldschmidt was this is a success also because the logistics, the remote system, everything was working so well. And now Thank you. And now I would now like to invite my friend Liz Sykes to tell you all about the next Goldschmidt in Chicago next year. So I am pleased to welcome you, Liz. Thank you.
As Catherine said, I'm Liz Sykes. I am the Vice President of the Geochemical Society, which is hosting next year's Goldschmidt in Chicago. And I am charged with bringing it to you along with the people that we've seen today. So the process has begun. We've set our themes. They are now visible on the Goldschmidt 2024 info website. It's going to be great science, and we are asking you to help make it so. We're calling for sessions. That starts on September 1st, and we need your ideas in by October 31st. And Chicago is a great place to have a meeting in the summer. The venue is right on the lake. It's accessible to the parks. You can get out on the water, and it's a wonderful family place with outdoor activities, and it's a hub of art and architecture. It's famous for the Chicago blues that are in many clubs around the area, and buildings like the famous Tower, the Art Institute, the Field Museum, and my favorite, our logo is the bean. And also, let's just have a little taste. Submit a session proposal, submit an abstract, join us in Chicago in August next year. Thank you.
And now back to the science. I have a question for you. Are you left-handed or right-handed? Also, the answer is a minor issue for all of us. It's of first importance for the amino acids. Indeed, each amino acid is chiral and can adopt a right or left form that cannot be superimposed on each other, like the right and the left hand. The fact is that all living proteins on Earth have chosen the left-hand form for the amino acids that make them up, and we are still ignoring why not the right-hand form. This is the big question Cornelia Meinert is dealing with, and which is leading her to track the origin of the life on Earth through the detection of chiral molecules in interstellar dust particles, comets, meteorites, and on the surface of other planetary bodies. Cornelia is research director at CNRS in a chemistry department in the University of Nice in France. Beyond chemistry, she's an explorer of the universe, a poetess and a philosopher. I let her opening your dreams. Cornelia, please, welcome on stage. And I pass you the word.
Merci. Yeah, philosopher, I don't know. So thank you very much for the interesting introduction. Thank you very much also for the organizer for setting up this wonderful event. I had a very great time. It's my first Goldschmidt and definitely not my last. I had plenty discussions on minerals, geochemistry. So I'm very glad for all the interactions I had during this week. And so congratulations for really this wonderful conference. I think you made all a wonderful job. And last but not least, I also want to thank you, the audience. I cannot really see you because the light is really in my eyes. But I see that some people are still there on a Friday. And I hope that you are not too tired after this intense week of scientific discussions to be a little bit curious about what we do in our research. And actually, I got already half of my introduction done. So I'm working on the origin of life, on the phenomenon chirality. So basically, we are interested in the origin of life. Sorry, there's water, yes. That started about 4 billion years on our Earth. And when life started, Earth was covered by volcanic activity. The atmosphere was rather hostile, so environmental conditions we would not consider to be suitable at the first place that life could arise. But still, the very first organic molecules started to assemble, formed larger structures that reproduced, evolved, and grew, and finally started the first life. And from this first life, billions of species followed, which is here represented by the phylogenetic tree on the left-hand side, so forming millions of species that we can nowadays observe in nature. And if we want to understand the very origin of the very first life, in my opinion, we should look in the ingredients that we can find in all life form nowadays on Earth. So molecules, features that we can find across the 3 domains of life. And this is indicated here on the right-hand side. So what all living species, independently if you're a plant, an ant, a human, what all those species have in common are that they use nucleic acids for the genetic code. They use proteins, so chains of folded amino acids, to catalyze and drive chemical reactions. And then we have in compartment the membranes that hold everything together. And they do much more membranes. Membranes can selectively shuffle in nutrients and remove waste outside of the cell. And proton gradients store and provide energy for chemical reactions. And then we have a 4th feature, which is homochirality, which is sometimes overlooked when we look in the origin of life. And this is actually the subject of my research. And we heard already something about chirality. And so for those of you that are maybe less familiar, this is your slide here. So chirality actually is a property not only of molecules, but also of objects, matter, and molecules. And we use this word chiral for any object or molecule if you have a mirror image that is non-superimposable on itself. And so the best example, as we heard, are our hands. I have a left hand, I have a right hand. Those are mirror images of each other, and I cannot superimpose them onto each other by any translational, rotational, or symmetry operations that I would apply. They would remain non-superimposable. And this is actually the same in organic chemistry. And I prepared some molecules, and this is actually when I thought this is a great idea. I didn't know that I will speak in front of such a big group here, so I'm more used to a classroom where my students would see what I hold in my hands, so maybe less useful here for you. So what I hold here in my hands is the smallest chiral amino acid, so this is alanine. And I have here in my left-handed hand the left-handed form of alanine, and in my right hand the right-handed form of alanine. And you can see, or maybe not, that those are, if I hold them right, that those are mirror images, and whatever I do, I cannot superimpose them. You agree with me that those molecules are very, very similar, and this is also the reason why their physicochemical properties are identical. They have the same boiling point, the same melting point, the same chemical reactivity in reactions. So they are basically the same, despite in the fact how they react with other chiral molecules and with polarized light. And so this is why it's quite surprising that at one point in the evolution of life, nature chose only the left-handed form and totally lost out using the right-handed form. So for all proteins, only left-handed amino acids are used, whereas in the nucleic acids, the sugar molecule ribose and deoxyribose is solely of the right-handed configuration. And this, we know this is called homochirality, so the exclusive use of only one-handed chiral molecules. And this homochirality is tremendously important for the three-dimensional structures of those biopolymers, for their functioning. However, we do not know why left-handed amino acids and not right, and why right-handed sugars are not left. And this is why I invite you now for, I have still 34 minutes, I invite you to a journey to follow me now on looking for where are the origins of life and this mystery about biological homochirality. And maybe we do not need to go so back far in time, neither so far away. We can stay in our own solar system and looking on our Earth. And due to astrophysical and geological studies that you presented here very nicely throughout the day, we can very well constrain, or approximately constrain, when life arose on Earth. And this was approximately 4 to 3.5 billion years ago. What we do not know, or where we have less information, is where the ingredients of life are coming from. So the building blocks that I showed you, every living species needs. And one of the most important experiments in the origin of life field was certainly the experiment by Stanley Miller in the 50s, who showed for the very first time that non-living matter can create organic molecules such as amino acids. And what he did is he simulated the early Earth's atmosphere. He reduced gases like ammonia, hydrogen, methane, and water. And even so, we know nowadays that the early Earth's atmosphere was less reduced. Follow-up experiments by researchers in the last years who used similar experiments with various gas mixtures that are more resembling the real early Earth's atmosphere condition always came to the same conclusions. If you use this lightning to simulate the lightning of the early Earth's atmosphere, you can create from simple gas mixtures inorganic molecules, organic molecules, alcohols, acids, and amino acids. And this experiment confirmed somehow the ideas that were outlined independently in the 20s by Oparin and Haldane, who independently from each other speculated that maybe life formed from a primordial soup. And even this idea was not new. Even this idea was already based and outlined by Charles Darwin, who wondered already why life couldn't have been created in warm little ponds. And while warm little ponds and surface areas are quite attractive because they give access to the energy sources that can trigger chemical reactions, we also know that the UV irradiation on the early Earth may have been too harsh for life to survive. And this is why there are several researchers that look for alternative locations on the early Earth, locations where you are probably more shielded against those harsh environmental conditions. And so this is an attractive model, would be hydrothermal vents on the bottom of the ocean floors. The advantage of hydrothermal vents, and also I heard several interesting talks during this week about hydrothermal vents, is that basically since they have this steep redox gradient, this energy storage can provide sufficient energy for chemical reactions to arrive. And then there is an alternative idea that some of the building blocks, probably not all, but some of the building blocks may have come from outer space and could have been delivered by meteorites to the early Earth, because also here we heard several talks about the late heavy bombardment, and so the accretion of outer solar material after the Earth has been formed. So when we look into this, and for those of you less familiar with meteorites, meteorites are stones basically that fall on Earth from outer space. Meteorites can have several origins. They can come from asteroids, they can come from a comet. And in those meteorites, there's even specific classes that contain a reasonable amount of organic carbon. And those are called carbonaceous chondrites. And so me personally, I'm more interested in those specific classes of meteorites. And if we extract those carbonaceous chondrites, the organic material, we see actually a huge suite or diversity of organic molecules, so indicated here with ppm values. So you can have hydrocarbons, carboxylic acid, phosphonic acid, any kind of organic molecular class you could find in meteorites, especially with the new techniques, analytical techniques that we have now in our hands in the laboratory. And in the end of this list, you also see that nucleobases, amino acids, and sugars. So the ingredients I previously talked about are so important for life to arise. And now if we have a closer look in those meteoritic amino acids, and we try to separate these two forms, the left and the right, and this is here a multidimensional gas chromatogram, and I can go in detail later if you want to learn about this technique. This technique helps us to resolve very complex mixtures, and it's also very much applied in environmental science, where you are also faced with complex mixtures. And what you can see here, the pointer is on. So what you can see here, the first two peaks correspond to alanine. D stands for the right-handed form, L for the left-handed form. Here you have the two enantiomer of valine, and so on. And what you maybe can see is that the L enantiomer is always a little bit more abundant, a bit higher. And if we precisely quantify those enantiomers, we actually can see that the amino acids have an excess, are enriched in the left-handed form. So the left-handed form that biology is using. And so this is why the idea came that not only organic molecules were delivered to the early Earth, but maybe also this preference for our left-handed amino acid and proteins arose somehow in space. Another object that we can study to get more insights in the origins of those molecules can come from comets. And I don't give a talk on comets here. Just briefly, comets are very interesting because they are very, very far from the sun, and because they are the most distant objects in our solar system, they may have preserved some of the pre-solar chemicals before our solar system was formed. And this is actually outlined here a little bit on the slide. So there is a biological evolution, but there's also chemical evolution in our universe. So we start from very, very simple volatile compounds. And this is something I learned in this conference, that volatiles for me are something completely different to what you as a geochemist speak about volatiles. So volatiles for me are already volatile molecules rather than the noble gases. So those volatiles get accreted and more complex during the evolution of the planetary formation systems. And so there is no surprise that there are several missions that target comets to get insights in how our solar system has been formed, but also which kind of organic molecules may have been preserved in those comets and can tell us something about pre-solar chemical evolution. And where there was one famous, one of the latest cometary missions, the Rosetta mission, and while there were several brilliant outcomes of this mission, I focus only on the outcome that has a direct link to my research, and this is that they detected in the coma phosphorus, an ingredient very important also for life, and glycine. Glycine is the smallest achiral amino acid used in the protogenic code in every living being. And this mission also wanted to land on the comet, which is indicated here by this lander. So they wanted to bring a laboratory on the cometary surface and look into the surface compounds, which kind of organic material is inside. They wanted to resolve the enantiomers, the amino acid enantiomers, and to look in any bias. Unfortunately, who followed this mission, the lander bounced several times, so then it was not feasible to carry out those experiments. And so this brings me to this slide that I would like to highlight you that cometary missions, we can learn a lot, but these are not missions that we can do every day. So what we can do in the laboratory is to study the chemical processes, because from remote observations, we learn a lot about these volatile molecules that can accrete on interstellar dust particles. Since there is a lot of water involved, we call those layers that accrete continuously on the dust particle, we call them ices, interstellar ices. Those interstellar ices suffer from radiation, energy impact by cosmic rays, UV irradiation, that can trigger further chemical reaction. In areas where it's a little bit warmer, those molecules and radicals can recombine to form even larger structures. What we are limited to do by remote sensing is to look in the specific molecules, which molecules can really form in those ices. And this is why several teams, including our team, try to simulate those complex chemical chemistries in outer space in the laboratory. So we create those interstellar ices. For this, we use vacuum chambers to create the same environments. We simultaneously create a gas mixture of volatiles that we know are present in those environments. So in our case, we used water, ammonia, and methanol. And as the energy source, we use Lyman alpha, because we know that this is one of the most abundant energy sources in space. And those experiments can be out several hours, several days. And if we look then into those ices, what we have recently done is that we found, starting from methanol, simple methanol and water ices, that in those ices we can form sugars. And one of the sugars that we found is ribose. So ribose, the sugar I told you, which the RNA is nowadays using. And because we are on Earth, there's always a risk of contamination, and we are all aware about this. And so that we know that the sugars that we form are really from our experiment and not from anything in our lab, we always label our methanol, this carbon source that we use as a reactant. We use carbon-13 labeled methanol, and this we can nicely, these are mass spectra of a standard and the mass spectra of the ribose that we detect in the ices. And those mass spectra really trace the carbon-13 signature, so that we can really confirm that those molecules are formed in the ice. And in the past, not only our team, but several other teams have done those kind of experiments to learn about the chemical evolution of those interstellar ices. And I think you can appreciate this result by a Japanese team who found nucleobases. So nucleobases, important for our nucleic acids in those ices. We found amino acids. Many other teams found amino acids in those ices. And very recently, we also found some phosphorus compounds, alkyl phosphates, phosphonic acids. And for those of you who work on phosphate, there is a huge debate in the origin of life community from where the phosphate is coming from. And this is something you know better than me. On Earth, on early Earth, most of the phosphate is trapped in minerals where it is not available immediately for pre-body chemistry. And so while I don't know if Matthew Parsek is still in the room, he gave a very, very nice talk, and he has nice ideas about reduced phosphorus species that are more soluble on the early Earth. Our idea is maybe to complement his phosphorus source with interstellar sources. And now I would like to come back to the initial question about how those molecules became selected of the specific handiness. And also here we have several ideas. I cannot go in detail into all those, and I picked 2 examples on which we recently worked. So one, this slide is for you. This is my only geochemistry slide. So I hope you appreciate the mineral depicted here on this slide. So this was a collaboration. Austrian geologist asked us to work with him together on the question if enantiomorphous minerals can enantioselectively adsorb organic molecules. And there are some enantiomorphic crystals, for example, quartz exists as left and right-handed quartz here on the left-hand side. And on the right-hand side, you see achiral minerals that can have chiral surfaces due to steps, kinks, and defects. And so they can enantioselectively adsorb molecules. While our outcome of this result was rather not really conclusive, I would say, and we would need to repeat those experiments. I invite everyone who is interested in working with me on this to come afterwards to me, and I'm very happy to exchange new ideas on the possibility of minerals driving the enantioselective selection. However, most of the time, we work on another model, and this is related to the finding that the L amino acids in the meteorite have this excess in the left-handed form. So there should be somehow a selection mechanism in outer space. And there are not a lot of possibilities. And one of the possibilities, which is also confirmed by observations, are chiral photons. Circular polarized light has been detected in molecular clouds. There are large regions where we have right circular polarized light and large regions where we have left circular polarized light. And left and right circular polarized light is also chiral. So you have a left and a right circular polarized light form. And this is depending on the electric field vector traveling either clockwise or anti-clockwise. So you have 2 different chiral forms. And since this light is chiral, it also interacts differently with chiral molecules. So what I told you in the beginning of my talk with the two enantiomers that are very, very similar and identical in a lot of properties, they differ in the way they interact with polarized light. So if those 2 enantiomers see now right circular polarized light, one of those enantiomers would degrade it photolized faster than the other, leaving an excess in the other enantiomer. And this is called asymmetric photolysis. And this process can occur in molecular clouds. And if we want to understand this differential absorption of right versus left circular polarized light, there's a technique some of you may be familiar with, which is circular dichroism. Circular dichroism is a very nice tool to look for chirality and enantiopurity of molecules. We use this tool to understand what is the efficiency of this chiral light to drive this selection between the molecules in this asymmetric photolysis reactions. And the circular dichroism itself cannot tell us the effectiveness. For this, we need to divide, and this is the most complicated slide, I'm sorry. You need to divide the circular dichroism by the overall absorption, which is non-selective. And if we just divide the circular dichroism versus the absorption, we get G, the anisotropy factor. And the anisotropy factor is telling us exactly this, how this circular polarized light can transfer its chirality to molecules. And so we see that this G factor, this anisotropy, depends on the wavelength, so it's wavelength dependent. And here I plotted alanine, in blue is a left-handed, and in red is a right-handed enantiomer. And we derived some equations from the fundamental principles of these interactions. And so we have an equation now, and this is plotted here on the right-hand side, that how much excess we can induce in those molecules during these asymmetric reactions. And this enantiomic excess that we can induce depends on this G that we can record and measure, and C, which is the extent of the reaction, so how long we do this photolysis. And with this principle in hand, we can predict what would be the outcome of this asymmetric photolysis of any chiral molecule. Without going too much in detail, this spectroscopy techniques, anyone who works with spectroscopy techniques knows that those interactions often depend on conformers, isomers, the environment that interfere with those measurements or change the response of a molecule. And because the chiral molecules in space can also be either in the water-rich mantles, can redesorb in the gas phase, so also here we are faced with different environments. And so in recent years, also related to the detection of glycine in the cometary coma, we know that maybe there can be an interaction of chiral molecules in the gas phase. We built a gas chamber to study those anisotropy spectra in the gas phase. And at the same time, we also developed sublimation sources to have films of isotropic alanine or any other molecule to simulate more the grain environment of those molecules. And so we have done those anisotropy studies for amino acids because amino acids, as I told you, are found in the meteorites. We have compared those spectra with other molecules, with hydroxycarboxylic acids that are also detected with excess in meteorites, and they show the same handiness, the same effect than amino acids. We have continued those research, and we looked into chiral molecules that have been detected by some of our colleagues from NASA Goddard in different meteorites, such as chiral alcohols, amines, monocarboxylic acids, where they didn't see any excess in meteorites. And this is perfectly in line with our predictions if we do this anisotropy spectra, because the anisotropy values are also very low, so the circular polarized light would also be not efficient to drive the selection in those molecules. We have looked into the effect of water environments. Recently, we looked into pH effects and salt effects that are present on mineral bodies that can change the anisotropy response. And as said, we also looked into the gas phase. And I picked one specific molecule to go a little bit more in detail into this asymmetric photolysis mechanism. So isovaline, some of you may have heard already about this. Isovaline is a non-proteogenic amino acid, so it's not in the genetic, it's not coded in our proteins. So this is why it's a good test case, because we can often exclude contamination. It's very rare on Earth, and if we find it on Earth, it's rather racemic or even in excess of D. But it has been found in huge excesses or reasonably high excesses enriched in this left-handed form. And another characteristic of isovaline is because it has here this methyl group compared to alanine, so it is less racemizing over time, so is keeping its initial interstellar enantiomic excess. Another characteristic of isovaline is that the enantiomic excess that we can identify in isovaline in different kind of meteorites that suffered different aqueous alteration correlates very well with the enantiomic excess that we see in isovaline. So in our community, isovaline is a kind of a good test case to look into the origin of chirality. And so you can guess what we did. We studied the anisotropy spectra of this molecule, so how it would interact with circular polarized light. And this was done together with Jana Boskova, very talented postdoc student in my laboratory. And together we recorded those anisotropy spectra. So again, you see the left and the right-handed isovaline form. And we performed photolysis experiment. For this, we have a laser set up in the laboratory that can create these chiral photons. And here on the bottom, you see a racemic non-irradiated film of isovaline. And you see how I hope that you can see that the quantities are similar, so we do not induce any enantiomic excess. We start with a racemic mixture. If we now irradiate this initial racemic mixture, we destroy one enantiomer more than the other, so that we can prove that these chiral photons can induce chirality into amino acids. And what we then ask ourselves is, when we do our ice experiments, where we create amino acids and sugar molecules, can we also induce a slight enantiomic excess when we create these ices, which we would call asymmetric photosynthesis? And so, yes, we were able, so by replacing this UV lamp, so Lyman alpha band, by a circular polarized light source, chiral photons, we could induce independently, or if we use left circular polarized photons or right circular polarized photons, we could create opposite handedness in the molecules that are formed in those ices. And so you can see that this asymmetric anisotropy spectra is really important for our work to understand this chirality transfer from these photons to matter, and that many factors contribute to this chirality transfer, and that we need to understand to better predict the CPL scenario in space. And what I haven't told you until now is that for now we worked with monochromatic light sources, but a few of you maybe in the room know that stellar sources are broadband sources. So we had another test case for this scenario. This was done on the molecule propylene oxide. Propylene oxide is rather not important for the origin of life. The importance of this discovery was that this was the first chiral molecule in space. While we could appreciate the detection, the remote detection of propylene oxide, for us, which was more important, that Sandra Pizzarello, a few years later, found this molecule also in meteorites, enriched in one of the chiral forms. So it has an excess in the R form by about 10%. So what we did? Anisotropy spectra. And so we could see that, yes, circular polarized light can induce chirality in propylene oxide. And this time what we were interested is if we would consider a broadband source. So what we did, we averaged over the entire anisotropy spectra to see the net effect of broadband circular polarized photons. And what we got is that if we want to result in an excess of the R enantiomer, the handedness found in meteorites, we would require left circular polarized light. So for us, it was somehow that we, for the first time, predict the handedness of the circular polarized light in which the chiral molecules that we now detect in meteorites have been illuminated with. And to even further test all our hypotheses on this chirality transfer and if this is really reliable what we do, we are very much looking forward to the asteroid samples that were brought to the Earth first by the Hayabusa mission, and this year by the OSIRIS-REx mission, because the wonderful thing about those samples is that they're even less contaminated than meteorites. In meteorites, we often hear the criticism, you look into amino acids, Connie, how you can exclude terrestrial contamination, and you are right. And so this is why those missions are so tremendously important. And so while they have brought back already the Hayabusa mission from the asteroid Ryugu, 5.4 gram for the analysis, which is rather a limited sample amount for the entire community to analyze. We are faced with several challenges that Vanessa in her talk very nicely outlined on Wednesday, and given that I have 7 minutes left, I speed up a little bit. I can give you already the results of one of the results of the Hayabusa mission is that when they extracted the organic material from Ryugu, they found different organic molecules, amines, carboxylic acid, and here, voila, our amino acids. Unfortunately, doing the analysis, also a recent review pointed out that the quantities that were used for the analysis were rather low, so that we cannot fully conclude about any enantiomeric excess in those amino acids. And what we are missing personally are sugars. What about the sugars? I told you we formed sugars in those interstellar ice analogues, and sugars have been very recently found in meteorite samples by a Japanese team. And why sugars are so complicated, without going in too much detail, and this is again the work of Vanessa Leva, who is in the room, and our former PhD student, Adrian Garcia, If you remember maybe your chemical textbooks back in high school, sugars are often represented by this linear form, but they are not in the linear form in nature. They do a cyclization. So this intramolecular cyclization can occur on the carbon 5 or carbon 4 sugar, so that we form either a 5-membered or 6-membered rings. This means if I look for ribose, I look at least for 4 different forms that can form in solution. So this complicates the analysis. This is maybe also the reason why it took so long to find those molecules in the meteorites. And this is something we are now very much looking forward, and this is again the work of Vanessa and Rafael Pepino in our laboratory, who developed very carefully the extraction and desalting fractionation tool. And thank you all, because we get very often inspired by environmental chemists who also are facing the same challenges of complex samples. So thank you very much for your tedious work on this. So we always pick a little bit from everywhere to build up our methodology. And so we also got the confirmation of this week to get samples from Rigoux, so that I hope that at the next Goldschmidt, and you can give me also a smaller room next time, I would also be okay, that at the next Goldschmidt I can tell you something about the enantiomeric excess in the amino acids and sugars in this very pristine Rigoux samples. I'm very much looking forward, and especially Vanessa, I think. And for sure, we continue our studies on this interaction of circular polarized photon to get more and more a realistic scenario. And if some of you may have seen, the enantiomeric excesses that we induce are rather low, a few %. We are also interested in how those small excesses can be amplified under prebiotic conditions. This is something we are currently starting to dive into. And we are also open for alternative scenarios, such as minerals, that could have maybe be the driving force for this selection. And with this, I'm almost at the end. So I want to thank my team in Nice. So Vanessa is here with me today. Jeremy is also here with me. And so I'm very grateful. Maybe a lot of PIs are saying this, but I'm relatively young PI. So I'm very grateful for the students that I had in the past, and I'm very grateful for all your dedication. And I'm also very thankful to 2 guys here on this picture. These are Sören Hoffmann and Nicholas Jones. Those are people with who I work half of the year in Aarhus, who help me building all the chambers. And those are physicists, so this also shows how important interdisciplinary research is. So I'm always coming, I want to study now molecules in the gas phase, how we can do. And they help me building up all those chambers. So thank you very much for those. And then we have here Louis Dondecourt and Ralph Kaiser, with who we do this interstellar ice simulation experiments. Almost done. And so if you are interested now in astrobiology and you want to join our community, I invite you to the very next conferences that are very soon. There is this International Society on the Study of the Origin of Life. We will have a conference in Quito very soon. And for the French community here, we have the French National Conference on Exobiology in November in Grenoble. And this is my last slide as a kind of thinking for you to have a thought when you go out of the room. So why not thinking about chirality as a trigger of the chemical evolution that led finally to the origin of life? That this is a parameter that we should not overlook if we think about and study the origin of life. Thank you very much.
Thank you, Cornelia, for this very exciting show and travel in the universe. Before starting the Q&A session, I remind the people who registered for the Meet the Plenary lunch that we propose to gather you at the end of this Q&A time, and we could go together to the room where if you want to meet Cornelia. We are welcome. Let's go. I open the Q&A session questions remotely. And here, I just remind you that there are a microphone at the top and at the bottom of the stair there.
Hi, Cornelia. Congratulations, very nice talk. So my question is very naive because I don't know anything about biology, but it's often said that life on Earth started only once and everything developed from this unique common ancestor. So is it simply possible that because life started only once, by chance, one of the two forms have been selected, and then, of course, because all the life is inherited from this unique common ancestor, then, you know, randomly we picked up one chirality rather than the other? Because what you showed about the asymmetry in meteorites and in space, it's very interesting, but it's a 10% effect, right? It's not a 99% effect. So basically, there are almost comparable number of right-handed and left-handed molecules available to start life.
It's not a naive question. It's actually what is discussed in the community. So you have a lot of origin of life researchers who think it was a random selection. So there was no trigger, no pre-selection required, and this was a random process. Why I believe this was not the case is because of this enantiomic excess that we see in meteorites. So maybe it has nothing to do with the origin of life, but personally I'm still interested in why those amino acids in meteorites had this excess. And then this 10% for an organic chemist, this would be huge. For amplification reactions, so there are famous amplification reactions. One is the SOI reaction, which can start from 0.001% and go up to 100%. So we don't even need to have 10%. There are certain reactions that can efficiently amplify.
Okay, so I didn't know that. Okay.
And this would be a little bit the idea that maybe this slight excess evolved afterwards into the homochiral state we have now.
Hi, thank you very much for the talk. I was just wondering, like, coming from the idea of primordial soup and that appearance of organic molecules necessitate some very precise conditions, do we know why there are some organic molecules inside the comets and where do they come from?
I mean, from my perspective, the chemistry in interstellar space is very constrained. So you start with a few molecules that are there. You have certain energy sources, so you can nicely almost predict the chemical outcome, which is also very random because you don't have a certain selectivity in the reactions. But yes, it wouldn't be a surprise since you have a lot of H2 and oxygen, so already the abundance of the element in the universe somehow tell you what kind of elements you will find in which amount in the cometary in comets, so that most of the compounds are water, form aldehyde, is not a surprise to me. It was still nice to detect this in situ in those comets, but I don't know if this answered your question. Yes? But maybe there are other rooms. Alessandro may be more suitable to, but for me it's not, has something to do also with the chemical abundance. So you have certain elements more abundant. So.
Hi. So I'm completely unfamiliar with this material, so I just learned a lot. Thank you for that. But the equation you put up for the development of enantiotrophy had a extent of reaction term. So is it correct that if it went to the reaction goes to completion, then the enantiomorphy would go away? And if so, then is there a degree of reaction where you'd get a maximum of this?
This is a very good question. So you really very well listened to my talk. So yes, this is a little bit a disadvantage of this asymmetric photolysis. So if you want to reach high enantiomic excess, which for you is just 10%, for us it's enormous. So if you want to reach this 10%, your photolysis rate would be 99.9%. So yes, you would destroy a lot. And this is why the complementary experiment, where we do this asymmetric photosynthesis, so where we do the ice experiments with the chiral light source, so this is the advantage where we can create them with an excess, where the excess is a little bit less, the extent is smaller, but this wouldn't be such a big problem in this amplification mechanism. But you're right, photolysis is destroying, so you will have not a lot left. But on a scale of, you will always reform also molecules. No? Amino acids are not once formed and that's it. No? There is a continuous formation of amino acids that could deliver an organic source. But I personally favor this asymmetric photosynthesis model.
Okay, thank you.
Thanks for the talk. I will go ahead before him. Do you think it could be that this difference between amino acids and sugars also developed to keep them somehow separate? Like the chemistries?
I'm not a pre-body chemist. I'm more a physical chemist. So what for us is now important in our upcoming research is we would like to see, or it would be a tremendous discovery if the sugars that are in meteorites or in samples of Rigoux would carry the excess of the D enantiomer. If now the sugar would be L, then we would need to find another hypothesis on where this came from and how this fits in this model. On the other hand, there are also prebiotic models that show that there can be a chirality transfer from sugars to amino acids, and vice versa. Amino acid can transfer their chirality to sugars, so that there is a mutual effect. And I'm not a big fan of separating things, because this was not the reality on Earth. In reality, we had complex mixtures, and this is what we have to work with. So there was clearly not one amino acid pool and one sugar pool. They were all sitting together and interacting with each other.
Thanks.
Thank you, Cornelia, for this nice, very nice review.
Thank you.
I am wondering, so this enantiomeric excess that is found in Cosmo materials, could we use it as a constraint on the origin of the organic material, when and where it was formed? You mentioned the interstellar ices. You mentioned the disk, which receive maybe a circular polarized light. And there are different, so it's more the question where, when, and then there is a question how. So you mentioned the ice chemistry, but there are other ways to form organic molecules via gas phase, liquids, etc. So what is your take on this?
I think we should sit together and make a project together, because this is a very good question. To be honest, I mean, for now it's for us very difficult because I'm also not an astronomer. So I'm constantly at meetings where there are more astrophysicists. I'm constantly asking them what would be the most realistic scenario for what I'm proposing. So would it be at the outer edges of protoplanetary disks, so where a nearby star would provide me circular polarized photons? Would it be in molecular clouds where the penetration of UV CPL is rather low? So this I cannot tell you. So I need astronomers telling me the best conditions. There is just one little thing that we see in isovalene, that the most pristine meteorites have a very small enantiomic excess. And the more they are aqueously altered, the enantiomic excess is increased. So this is somehow used in our solar system, but cannot tell me something about this initial origin. But in the solar system, they use it a little bit to distinguish between meteorites. So what is the aqueous alteration on parent bodies? But I think we will speak afterwards. This is a very, very good point.
Join us afterwards if you want, no problem.
Is this your
Yeah,
time for talk?
yeah, go.
Okay, thank you very much for your presentation. I got more technical question. I'm analytical chemist, and I'm always worried about contamination. And
Me too.
as mentioned in your talk. But we know that most of them chondritic meteorites, they are finds and not falls, meaning that they've been sitting around for a while in museums and somewhere. So how can you actually exclude any contamination which happened, or how can you distinguish between which was there originally and what came in later? Or is there anything which came in later? Is there?
I'm also just we started to develop now analytical protocols to look into meteorites, but there are several experts also in the room. What you can do is to look in the isotopic ratio. So if you have an enrichment in the higher elements, you clearly can see an extraterrestrial origin if you are enriched. If you have clearly isotopic signatures of Earth amino acids, then you know that this is pure contamination. Isovalene is a non-proteinogenic amino acid. This is why often we focus on isovalene only rather than alanine, phenylalanine, that I have to admit I saw in some of the samples with high L-enantiomic excess, and I don't believe that this is coming from the meteorite, but contamination. But in some meteorites, or depend how much amount you get, you cannot have sufficient material always for the isotopic measurements. It's very difficult. So this is why these RIGU samples are so important. It's beautiful to have them for those kind of studies. So you can rule out with isotopic studies and to focus on molecules that are rather rare in the biosphere.
Hi, thank you for your talk. I'm just wondering if you have also tried with other radiation sources like ions or electrons, especially because, I mean, here you focus on cometary material, but it can be interesting, for example, for icy moons.
Yeah, so me personally not, but in the collaborations I work with, Ralf Kaiser in Hawaii, he uses preferably electrons to simulate the secondary electrons of cosmic rays to trigger his reactions, and the outcome is very similar. What we need is sufficient energy to drive the reactions. We do form with an electron gun or Lyman alpha benzos. We create amino acids, sugar molecules independently of the isotopes. Maybe the ratios will be a little bit different.
Yeah, you create the molecules, but are they also racemic or non-racemic?
Okay. If you use an achiral source, racemic. If you do not have a chiral source, they would be racemic. It's 50-50.
Hi, thanks for the great talk. Up here.
What? At the top of the stair there.
Here.
Okay, hi.
I was wondering if like the excess of enantiomer could lead to isotopic fractionation.
Sorry?
I mean, does the excess of enantiomer can lead to isotopic fractionation?
I saw a paper on this. Not to the extent that we see it. There are, because it's very, very low. So it's with the current methods wouldn't be measurable. I couldn't say it's completely outruled, but the effect is very minor.
Okay, thank you.
I think we are done with the question. You have one question? Yes, go. No remote, no.
Probably another very naive question. I noticed in one of your slides, I think you showed the enhancement factors for the same experiments with the right and the left light, and the products were not equal. In one of them, it was like 0.7% enhancement, and in the other, it was like 1.3%. So I'm wondering if you've got, a particular environment with a particular chirality of the light, whether actually that environment will enhance the right-handed chirality in some molecules and the left-handed chirality in other molecules.
No, the point is these are experiments. So we try to monitor and to keep since it's two different experiments, one's using left circular polarized light and in the other experiment right circular polarized light. So we try to reproduce the same conditions. But as you know, in the laboratory, it's not always feasible. And those experiments, these asymmetric photosynthesis experiments, were done at a synchrotron source. So we had very limited time. And I can even imagine that since one sample was irradiated for 36 hours and the other 34, simply because our beam time was ending. So what we do with our experiment in the publications that we have, we can correlate this to the photon dose that we put in the ICES, so that this is showing that the result should be symmetric based on the chiral photons we put in the system. So we would expect symmetry in those results, but because it's experiments, we couldn't achieve it.
Thank you.
Yes, that experiment limited. Oh, Silke.
Hi. I was just wondering, because there have been two interesting primitive meteorite faults in the past in Germany and the UK, if you could maybe check for those, because they were picked up just 24 hours after the fall.
Yes, Vanessa is eager to analyze those samples. Yes, it took us much longer to develop those protocols to minimize contamination, to know the recovery rate. So Vanessa can speak hours about what she has done in the laboratory. And after her talk, we had also this question. So if you want to give me the samples, I have a suitcase here. I take them home immediately. It's no, this is really something we would like to do.
I think the people who have material.
They are here in the room.
You can introduce them perhaps later.
Okay.
Yeah,
Yes.
but this is probably an interesting bargain. I have a question, actually. It's a more technical question. I was definitely impressed by your simulator of what's happened in the universe. And I wonder if you designed it, if it's unique, or if there are other systems like that in other countries.
There are many. It became really popular, I would say. This laboratory.
You did it? You did it? The first one? It was
No. The very first one, in my opinion, was Greenberg. In the 70s, and Louis Dondecourt was his PhD student at that time. So I grew into this community by Louis Dondecourt, who was one in this community of one of the first. But nowadays you have research teams, a really good research team in France, in Spain, in US. So these ice chambers itself are not unique. Everyone has a little bit another system, using different energy sources, focusing on other gas mixtures, using even lower vacuums than we use it in our experiments. Temperature differ from 20K to 80K. So depend a little bit also where in the universe at which system you look at. But it's not unique, and it's a popular theme at the moment. So
Okay.
there are a lot of PhD and postdoc opportunities.
Thank you very much. I think we can close this Q&A and applaud Cornelia again. Very, very exciting science. Nothing remote. So we are going to building A, room 4 in Rhône level, first level. Okay, so those who don't know where we are going, please join us, and we will have this casual lunch.
Ouais, mais j'ai réalisé, c'était trop petit.
Ça, c'est génial.
Mais c'est trop petit.
C'est trop petit, mais c'est pas grave. Il y a sûrement une très belle photo de notre photographe.